All right, so now that we've gone through the basic introductory and review from grade 9, what we're going to do is we're going to start into the regular course material. Now this 1.0 unit, like all point .0 portions of every unit, are going to be just to kind of introduce you to the topic. And typically speaking, you're going to be doing these on your own, either immediately following a unit test, or on your own at home the night before the first lesson, the point .1 version of every unit. But for the first time, I'm going to walk you through this and just kind of get you started. Now, the idea of modeling linear relations is the idea of creating equations from verbal descriptions or textual descriptions. The idea is to be able to come up with a mathematical model for these various situations and scenarios. Now, in order to do that, we have to be able to break down the English language. And of course, in the English language, there's so many different synonyms that mean the same thing. So here's a list of common words that we see in various descriptions in mathematical word problems or just everyday life. So what we're going to do is we're going to categorize every one of these words into one of the possible mathematical operations that we typically use: plus, subtract, multiply, divide, exponents, and equality, equals. So for each one of these, we're going to give a quick little look at it and kind of analyze it. So a lot of them are very obvious, and some of them are you have to kind of think about a little bit. But in the end, they'll be pretty straightforward, and you'll be able to apply it hopefully later on. So of course, when we're talking about plus, that obviously means to add. So we'll just put a little plus sign here. Decreased by, of course, decrease means go down, so this must mean subtraction. Is, well, we're stating that something is something else, so this is going to be equality. When something is tripled, it means it's multiplied by 3. Results in, that's another way of saying, well, that's equal to. Okay, these are all pretty straightforward so far. Doubled, that means something is multiplied by 2. When we have something that's more than, that means we added to it. Of, we're multiplying. Times, we're multiplying again. Cubed, this means that we have an exponent to the power of 3. So we'll just write like a little EX here for exponent. Minus, of course, means subtraction. Increased by, we're adding. And then we're adding onto something, as in this and then that. So we're adding. Ratio, that's another way of really saying a fraction. So this is just division. Squared, of course, that's an exponent. Difference, the difference between two numbers means that we're subtracting them, so this must mean subtraction. Gives is another way of saying equality, so this is equals. Sum is the word for the total of adding a number of items together, so we have addition here. Less than, that means we're going down, so that must mean subtraction. Of course, total definitely means equals, that's a nice and obvious one. Average. Well, remember how you got to calculate average. You got to take all your values and then divide it by the number of items you have. So this is actually going to be a division. Share, we're sharing amongst things, so this is division as well. Quotient is, of course, the solution to a division problem. To the power of, that definitely means that it's an exponent. And then product, of course, is the answer of multiplying multiple things together. And that's it. Those are all the words we learned, and we're looking at 25 different words. A lot of them are pretty straightforward, and hopefully you knew the bulk of them. Let's get into, we're going to go a little bit deeper now, and we're going to try and take scenarios and create solutions to these, or we're going to try and model these scenarios into mathematical problems. So going all the way down to the next page, when I say model, what I mean is I'm going to read a scenario, and I have to define what the unknown values are in that scenario. Remember, unknown values are our variables. So we're going to create let statements, like any word problem like we've ever done before. We have to let some variable represent something in the equation, something in the mathematical problem. And again, it must be the unknown or the unknown values, one of the two. Okay? From that statement and the description, we should then be able to create an equation from it. So if we look at the first one that's giving to us, it says the sum, sum. So that must mean, so where's my little highlighter here? So the sum right here, the sum means to add. Okay, what are we adding? We're adding two numbers. And we know that the sum is 15. So the total of this, the total of the sum is going to be 15. So we know we're adding and we know we're calculating. Is means equals. So that's why we have our plus sign, we have our equal sign over here in this equation. So what are our variables? Well, it's the two unknown numbers, whatever these numbers are. So let's think about these let statements. Let x, just some variable name. We can use whatever letter we want as long as it's clear. Let x represent one of the numbers. And let y represent the other number. That's about as easy as it gets, because the only description we have of these two numbers is that they are numbers. We don't have anything related to them within the problem description, so we can keep it nice and simple. Let x represent one of the numbers. Let y be the other number. Great. Now with this, we now have our variable names, and we have a description of the operations. So in that case, we can now create our equation. Let's say the sum of two numbers. So the sum of x and y, so that means x plus y, is equals 15. And there's the 15 at the end. So this is what we want to do throughout all of them. So let's look at the next problem. The difference of two numbers is 10. This is the exact same problem, but now we're talking about difference, which of course means subtraction. But other than that, it's exactly the same. So we can describe our variables in the same way. So I could say let x, you have to pardon my handwriting here, instead of writing represent, I'm going to keep it nice and simple. Let x be the first number, or let's say the larger number. Now you might be like, why do you want that one to be the larger number? Well, when I'm finding the difference between two numbers, I really want to find kind of like the distance between them. And in order to make sure that that number is a positive number, I want the first number to be larger than the second number. So for example, if I have 7 minus 5, that's going to give me 2. But if I do 5 minus 7, that gives me negative 2. So we want to keep that difference to be a positive number. So we want the first number to be larger. All right. So let x be the larger number. Let's let y be the smaller number. Let's see here. Alrighty. And now we have to create our equation. We know it's a difference. All right. We know it's the difference between these two numbers. It's x minus y. And we know the difference is 10. So we have our value of 10 here. Okay. So all of these problems are going to be the same idea. The length of a rectangle is 3 centimeters longer than the width. So I still need my let statements. What do my variables represent here? Well, they represent the only two unknown values we have in here, which is the length and the width of this rectangle. We don't know what those are. So let's figure them out. So I can use x and y again, but just to show you that I don't have to, I'm going to use something that's a little bit more relevant to the problem. Let's say let L be the length of the rectangle. Let's say be the rectangle length. And let's let W be the rectangle width. There we go. Now it says the length of a rectangle is 3 centimeters longer than the width. So the length of the rectangle is equals. The length is 3 centimeters longer than the width. So that means the width plus 3. All right, there's my formula. That's all I need. There's my equation. All right, now the problems are going to get a little bit more challenging. So we have 5 times one number plus 4 times the other number is 24. I don't have any real descriptions about the numbers other than the fact that they're numbers again. So I'm just going to use x and y, and I'm going to keep the description as simple as possible. Let's say let x be one number. And let's let y be the other number. Let's say, we could say, yeah, we just say the other number. There's only 2 in this case. All right. Now it says 5 times one number. 5 times one number. So let's say 5 times x plus, all right, plus 4 times the other number. So 4 times y. So 4y is, so that's equals 24. There's our equation. No more to it. All right, let's keep going down. Oh, we got 3 more here. So the total value of $5 bills and $10 bills is $80. What do we not know in this question? We know the value of the bills. We know the total amount of money. But we don't know how many of each bill we have. So that is our unknowns. Those are our unknowns, I should say. So let's say let x be the amount of $5 bills. So the number of $5 bills, the amount of $5 bills. And so that means y will be the amount of $10 bills. Now, if you think about this, if I have a wallet and I have a whole bunch of 5s and a whole bunch of 10s in my wallet, and I know that the total amount of money I have is $80, basically I have to add up the number of 5s and the number of 10s. Okay, so let's say, for example, I had 4 $5 bills, so that would take up $20, and then I have to fill the rest out with $10 bills. So that would mean that I would have 6 $10 bills. That would give me $80. In this case, x and y represent the quantity. So we have something x and something y. Well, what is it? Well, we're talking about the total amount of money. So I need the value of money for each one of those. So $5 times x $5 bills. So we have $5 plus $10. So 5x plus 10y. So I have x $5 bills plus y $10 bills, and my total is going to be $80. Okay. Let's go to the next one. This one is a little bit trickier because we have to kind of go back to our knowledge from elementary school a little bit here. So in this one says some money invested at 6% and some money at 4% together earn $25 in interest. So this problem is pretty much the exact same as the previous problem. With the unknowns that we have here is the amount of money for each percentage. Just like the previous problem was the amount of bills for the dollar value. This one is the amount of money for the percentage. So it's still really the exact same problem. So we say, let's say let x be the amount invested at 6%. 6%. Okay, and we'll do the same thing for y. Let y be the amount invested at 4%. Great. I still have to create an equation for this. I know the total is going to be $25. The combined total of both amounts is going to be $25. So I got to add them up, and it's going to be some multiple of x. So x is the amount of money invested at 6%, plus some amount of 4% dollars is going to be equal to $25. Okay, or 4%. $25. What number goes here, though? I can't really write 6%. 6% times x. That doesn't, we can't really create an equation like that. So what's another way of writing 6%? Well, remember what 6% actually means. It means 6 out of 100. Or another way to write that is we do that math, that's 0.06. Similarly speaking, 4% is 4 out of 100, which would give us 0.04. So let's use those numbers. Those are actually numbers we can work with in our equation. So 6%, which is 0.06 times x, because that's the amount invested at 6%, plus the amount invested at 0.04%. Do the math here, and we can get our full equation. All right, one more. Just one more. The cost of 7 milkshakes and 10 donuts is $86. With an extra typo of an extra dollar sign here. Okay. The cost of 7 milkshakes and 10 donuts is $86. What are our unknown values here? Well, think about it. We know the total, we know the quantity of each element, but we don't know the cost of each thing. In our previous statements, we knew the cost or the value of each thing, but we didn't know the amount. Here it's the opposite. We know the amount, but we don't know the cost. So our unknowns are the cost this time. So let's say let X be the cost of a milkshake. Of a milkshake, a single milkshake. And similarly speaking, we're going to say let Y be the cost of a single donut. Okay, so we need to set up our equation that was really just a total cost here. We know it's going to equal $86, but what's going to equal $86? 7 milkshakes. Okay, so that's 7 times something. 7 times the cost of a milkshake. So if I bought 7 milkshakes and they were each $1, it cost me $7. So this is 7x. And now I got to add on to that the number of donuts I bought. Well, I bought 10 of them. How much did each one cost? Each one cost y. So 7x plus 10y is going to be a total of $86. Put this into perspective. If you went to, let's say, Krispy Kreme donuts, and you bought 7 milkshakes and 10 donuts from your friends, and it cost you $86. Basically, what we're trying to calculate is, well, how much was each milkshake and how much was each donut to get you up to $86? So now that we have got lots of practice in modeling our equations, we can now apply this to real problems. So in this case, given the following linear relation, which is just our equation, a linear equation here, use a left side right check to determine whether the given points are on the line. That's not really related to these above things per se, but it is still something that we need to be able to do. So if we're given this equation, this 2x minus 5y is equal to 10, we want to know if this point, 10, 2, is on that line. Don't worry about what the line actually looks like right now. Let's just pretend that the line is, where's my pencil here? Let's just pretend that the line, let's say the curve is like this and the line goes across. We want to know if 10, 2, maybe that's right here, who knows, is actually on that line, or is it over here somewhere, or over here, or over here, or over here. When we say that 10, 2 is a solution to this problem, it means that it's actually on the line. So if we do a left side, right side check, and we just substitute these numbers, so the 10 goes in for the x, and the 2 goes in for the y, if we get a match for the left side and right side, that means that this point is physically on the line, which means, yep, it is a solution to this problem. So let's try this out. So we have 2 times 10 plus 5, sorry, not plus, minus 5 times 2. And on the right-hand side, we have 10. So 2 times 10, that's 20. Minus 5 times 2 is 10. 20 minus 10 is 10. So yes, they match. So left side is equal to right side. So I could even do a therefore statement here. I could say since is an upside down therefore statement. Since left side is equal to right side, therefore 10, 2 is on the line. Sometimes we'll call that an intersection point. All right, same idea. So we want to see if 5 comma negative 4 is on that line. So again, we do the substitution. So we're going to put 5 in for x and negative 4 in for y. So we have 2 times 5 minus 5 times negative 4. And we want to see if that whole thing is equal to 10. Well, let's find out. 2 times 5, well, that is 10. Minus 5 times negative 4. That's minus 5 times negative 4, so that's minus negative 20. Well, a minus of a minus, that's an addition. So that's really going to give me 30. Does 30 equal 10? No, it doesn't. So in this case, left side does not equal right side. So this point does not exist on the line. It's somewhere off it. So in this case, I could do my final statement. Since left side does not equal right side, 5 comma negative 4 is not on the line. There we go. So that's where we're going to stop on 1.0. This is going to give you the basic foundation you need for the rest of the unit. If you're comfortable with this, great. If not, take some time and try and go over all of these questions on your own and see if you can get the end results that we did here in the video. Thanks.